Hello, my name is Victor Lopez Pastor, and I want to give a talk about arbitrary optical wave evolution with Fourier transforms and phase masks. A unitary transformation is a linear transformation that preserves the norm. In physical terms, this could represent an ideal linear optical transformation without loss. But how can we implement any unitary transformation? We know that for the 2x2 case, the solution is simple. It's just a beam splitter. But we would like to generalize this idea to any number of modes. In other words, we would like to be able to realize a programmable universal multiport interferometer. But why would we be interested in such a device? There are many applications in which one needs to implement controllable unitaries on a very large number of modes. To give an example, boson sampling. In a seminal paper in 2013, Scott Aronson showed how to realize quantum supremacy by implementing a random unitary transformation on n photons. Another example, with a sequence of unitary transformations and optical nonlinearities, one can construct a quantum optical neural network that could have many applications in quantum machine learning. But for these applications and many more in photonics and quantum information processing, we need the ability to perform unitaries on a very large number of modes. So what was the previous solution to this problem? In 1994, Reck et al. Showed how any unitary can be realized with a photonic circuit made out of m-square beam splitters. Then in 2016, Clemens improved a little bit this solution by showing a more compact photonic circuit that is a mesh of beam splitters in a square array. The problem with this solution is that it's difficult to scale up. It's difficult for technical reasons to build a photonic circuit made of a very large number of beam splitters. And when m grows, the number of beam splitters grows quadratically, which makes it very hard. So one idea is to use a sequence of Fourier transforms and phase masks. Fourier transforms are very easily implemented in optics. For example, with a lens, we know that for any input image in the Fourier plane, we will obtain the Fourier transform of the input image. On the other hand, phase shifts are also very easy to implement, for example with spatial light modulators, and furthermore we can control it. This idea has been realized experimentally for some particular unitary transformations, but we would like to know how to generalize this idea for any unitary transformation. In our case, we focus on the discrete Fourier transform because it will be more amenable for the mathematical treatment. For our purpose, the discrete Fourier transform is just a fixed unitary transformation, while the phase mask is a layer of controllable phase shifts. Then our setup will be a sequence of a Fourier transform followed by another phase mask, again a Fourier transform, a Fourier phase mask, another Fourier transform, and so on. So we know that such a decomposition is possible for any unitary transformation. This is a result by Borevich already from the 50s. But we would like to know if we can make an efficient decomposition. So in other words, we would like to know how many phase masks we require in terms of the number of modes. And we also would like to give a procedure to find the adequate phase shifts to implement any unitary. Mathematically speaking, the discrete Fourier transform can be represented by a matrix that I present here. And the phase mask is just a diagonal unitary. So it's just a matrix that is diagonal and whose diagonal elements are complex phases. So then I present here our main result. We show that any unitary matrix acting on m modes when m is even can be decomposed using 6m plus 1 phase mask and 6m discrete Fourier transforms. The idea for our method is in fact very simple. We already know from the work of Clemens et al. That any unitary transformation can be realized with a sequence of beam splitters. So we show that any two layers of beam splitters, any two layers of beam splitters in the construction by Clemens can be realized with 12 Fourier transforms and phase masks. Then decomposing any pair of layers in the construction by Clemens, we show that any unitary with m even is possible to decompose it with a sequence of 6m plus 1 phase mask and 6m discrete Fourier transforms. Then just by parameter counting, one can see that this has an optimal scaling in the number of phase masks required. But then one could argue that the discrete Fourier transform is not exactly the same as the integral Fourier transform that one finds typically in optical setups, like with the lens that I described before. Then it's a legitimate question whether we can actually perform the discrete Fourier transform with an optical device in a simple manner. But we show that indeed it's possible. Consider a planar waveguide. Let's say that we inject a superposition of wave packets on one side. At some propagation length, we will obtain another superposition of wave packets, and the amplitudes of these wave packets will be related to the input wave packets by a unitary transformation S, which in fact we can show that is nothing else than a discrete Fourier transform up to a permutation of the channels and phase shifts. So we showed that we can produce any possible unitary transformation with a number of phase masks that scales linearly with the number of modes. Then we know that we could use that for boson sampling. But the question is, do we really need so many phase masks? Do we really need to implement a general unitary? And we show that, in fact, just with one discrete Fourier transform, one phase mask, and another discrete Fourier transform, the probability distribution of the photons, it's already impossible to simulate with a classical device. So we can show quantum supremacy with such a simple photonic circuit. And this is the result of another paper that is currently in preparation. So to conclude, we show how to decompose any unitary transformation with discrete Fourier transforms and phase masks. We also show that the scaling in the number of phase masks is optimal. And Finally, we proved that one can show quantum supremacy with just 2 discrete Fourier transforms and 1 phase mask.